Hello everyone, welcome to ARC 309, where we show you how to architect a high-throughput asset tracking application. My name is Fernando. I'm a senior specialist solution architect on AWS for mobile and front-end technologies. And I'm here with my friend Rafael today.
Hi everyone, my name is Rafael Leandro Jr. I'm Global Solutions Architect for Consumer Packaged Goods and Transportation at AWS.
And in today's sessions, we'll walk you through how to tackle common technical challenges related to building a high-throughput solution for asset tracking, and how we were able to achieve success by using a combination of AWS services in doing so. And we have a very simple agenda for you today. First, we'll be talking about use cases for asset tracking applications and why they are important. We'll also be focusing on challenges that consumers face when building and testing solutions that require high throughput. Then, we'll cover the solution, the technology used, and architectural considerations around it. Finally, let's go through a very important piece in any solution that needs to scale and maintain its integrity: simulating. Let's start by talking about applications and the challenges faced when building asset tracking solutions. First, we need to understand that today location data comes from everywhere: vehicles, buildings, satellites, networking appliances, mobile devices, tractors, landmarks, wearables. You can really observe that it is estimated that by 2025, the location-based service market is expected to be worth $39.2 billion. That's a big growth from what it was worth in 2020, which was $17.8 billion. That amounts to a 17.1% growth per year. And why do we track assets? Well, the easy answer is to make informed decisions based on the data provided by them. Pick a vehicle, for example. Maybe an oil temperature of 230 degrees Celsius is enough information for a driver to be really okay with how the vehicle is performing. This data can indicate much more though. It could indicate that, well, based on this temperature level, the weather, the road conditions, and maybe the amount of time that it is taking for the oil level to drop, that this vehicle needs to go under maintenance ASAP. Understanding the current location of an asset and how far they are from a destination is also crucial for businesses to make decisions on operations. If I know that a truck is 15 minutes away from my loading dock, I can start preparing the personnel and the area to receive my goods. Having the ability to adjust my area beforehand can increase my productivity by a lot. And if you have the information on where your assets are and for how long they're staying in certain areas, maybe you can determine if assets are constantly idle or working for more time than expected. This, paired with sensor data, can give you a big advantage in understanding exactly how your assets are performing, and you can really understand if they're currently under maintenance, functioning really well, or even if they need to be replaced. And of course, tracking assets provide a myriad of challenges from a technical perspective. Think of it this way. Imagine back in 2012, not that long ago. You got a requirement to build a solution that needed to receive data from 50 trucks via SOAP API calls every 5 minutes. You went ahead and created a solution hosted on 2 load-balanced virtual machines connected to a single database instance. You had to manage all of that infrastructure, of course. OS updates, antivirus, database patches, everything. Hardware really becomes obsolete very quickly, right? But you're powering through. Everything's working. That worked out at the time, but time changes, technology evolves. Maybe you're now supporting 150 vehicles sending data every 2 minutes. And you have a lot more people interested in the data. So maybe you have created a replica of your database for only read-intensive tasks. And you really changed your monolithic application to support not only SOAP, but REST APIs as well. But everything works, but things change to break more often. One day, you get a message from the CIO. Solution's amazing. Let's use it to track all shipments in the company. all 150 shipments. What do? Business challenges aside, there's a number of technical challenges that you're not prepared for. Your infrastructure is the same since 2012. Is that enough to receive this amount of data? Can your monolithic application scale to consume 100 times more data than what it is expecting? How would the performance look like? How are you onboarding new vehicles extremely quickly, guaranteeing that, well, traffic remains secure and never leaves your database or your project, unless it's really allowed to? How are you making sure that as your traffic scales, that you're keeping identity and access management under control? How many people can manage your solution? Who can deploy your application or play with your infrastructure? By the way, can your database with a single read replica handle all of this load? How do you answer this question? How can you test it? Are you ready to reproduce data coming from hundreds of thousands of devices? And that's the use case that we chose to present a solution for. It relies on vehicles as assets. We chose vehicles because they are able to produce a very large number of sensor data and they are constantly moving, providing us the ability to add tracking capabilities into our solution. The telemetry data comes from fictitious sensors: speed, acceleration, torque, oil and fuel level, things like cars, things that cars have. And all of this data is perfectly into monitoring and adding a solution that will be presented not only to address the high scalability, but to dig deep into the details produced by each vehicle. And all of that is part of a simulation engine created by us to consume millions of requests per minute. Now I'm going to pass it over to Rafael, who's going to talk to you about the solution.
Thank you, Fernando. To present the solution, we'd like to start with a demo, and then we'll return back to the deck to explain the architecture design and the logical flow supporting the solution.
This is our solution demo. On the right side, we have a simple web application including a map. On the left side, a monitoring dashboard, where we'll see all information regarding the vehicles. This demo is prepared not only to receive data from real vehicles, but also to simulate those vehicles for testing purposes. So let's say you have 20 trucks in your fleet going from your distribution centers to the retailer sites, for instance. And of course, you'd like to track them. So let's include those vehicles here. Vehicles, all right. The solution generates a route for each vehicle, also including a geofencing area. As an example for this demo, each geofence will represent an area around the distribution center where the vehicle just left. The vehicles are popping up on the map right now and sending data, as you can see on the monitoring dashboard. Let's take a look closer at one vehicle to see it moving on the map. So let's pick one vehicle here. Just need to zoom in. Okay, a little bit more. Let's see more. All right. Okay, so the vehicle is running and updating its position on the map properly, right? Although the routes are dynamically generated by the solution, the vehicle positions are real following the given route, which enables us to receive real latitude and longitude pairs to make the simulation more similar to the reality. Let's zoom out here to see more vehicles on the map. All right, that is good. That is good. Okay, so looking at the monitoring dashboard, you can see the number of vehicles running. You can also see the number of geofence events, which means in this case that all those 20 vehicles left the distribution center area. We also can see the number of location events and telemetry events that we are receiving per minute, right? So with these numbers, we can say that we are receiving almost 3,000 events per minute, including location and telemetry events for those 20 vehicles. Below some critical information we decided to monitor closely. which includes a list of the highest speed vehicles, a list of the lowest fuel level vehicles, and a list of the highest oil temperature vehicles. If you'd like to see more information about any specific vehicle, you can just click on the vehicle, such as this one, for example, with the highest speed. And here you can see all metrics about that specific vehicle in real time, including its speed, oil temperature, fuel level, the positions within the last minute, and so on. Let's move back to the main dashboard. Okay, so now imagine that one of your vehicles is in a high risk by running with an extremely low fuel level, for instance. In that case, we expect to be alerted so we can take actions immediately. So let's simulate that and put the mobile phone in the screen in order to wait for the message. So let's put the mobile phone here first. All right. Now let's select one vehicle here on the map. Let's pick this one in London. We selected this. We can see the VIN number start with 9J9, and let's simulate the low fuel level. Okay, so as you can see, the vehicle pin just changed its color to red, so it represents a red flag in the map. And also you can see the same information in the lowest fuel level vehicles. That specific vehicle is showing with 1% of fuel level, which is a high risk, right? Regarding the text message, in our mobile, we just received a text message with alerting about that high risk vehicle with the VIN number, the fuel level, which is 1%, and also the position for that vehicle that you can open and click on this and see the right location of that vehicle. All right, let's move back to the dashboard here. Okay, so we tested the solution with 20 vehicles and we received about 2,900, 3,000 events per minute. But what if you have 100,000 vehicles? Let's onboard those on the map. Let's onboard 100,000 vehicles here. You will see more and more vehicles popping up on the map shortly, and also the updated information on the monitoring dashboard. Everything in scale tends to be more complex, right? You need to deal with the underlying resources for scalability and many other factors. That's why building a resilient and our scalable architecture is important. Doesn't matter if you have just few vehicles sending 3,000 events per minute or thousands of vehicles sending 30 million events per minute. You can build an architecture that keeps up with your growth and your new load. So now you can see that we have almost 100,000 vehicles, it's counting, and we are receiving now about 20 million, 25 million events per minute. So here we have a high throughput solution that can receive a large amount of events each minute, right? Yeah, so now 35 million events per minute. Okay, so additionally to that, it's also important to monitor the underlying infrastructure supporting the solution. In this dashboard, we are monitoring important metrics for Lambda functions in the solution, including errors, throttles, service limits, and any other issue that can impact the solution. And you can see with this graph here, when we just leverage 100,000 vehicles, we can see this graph, this peaking right here. All right, so let's go back to the main dashboard. All right, all those geofence events, we just received all of them. Okay, so we now have 100,000 vehicles running, about 30 million events per minute. Okay, so let's go back to the presentation deck to understand how the architecture design and the logical flow look like.
Okay, so let's walk through the architecture design for the solution. We'll dive deep into each specific flow in the following slides, including why we choose each specific service. But the intention for now is to provide you the big picture and the vision of what we are using. The fleet of simulated vehicles send their telemetry and location data over MQTT to AWS IoT Core. Those messages are filtered using IoT rules and sent to different services depending on the case. For example, the IoT rule is responsible to capture all messages and store them in a time series database with Amazon TimeStream by leveraging its built-in integration, so we don't need to write additional code for that. All the location messages coming from the vehicles are sent to a Lambda function where two actions are performed. First is the geofencing validation that checks if the vehicle entered in or exited a predefined area of interest, or geofence, which is one of the Amazon Location Service features. If so, it generates an event in Amazon Event Bridge that triggers a Lambda function responsible to store that in the TimeStream database. The second action is to register the new vehicle position in the AWS AppSync, which will generate a mutation and store the new position in a DynamoDB table. That mutation in the AWS AppSync is captured by the application via AWS Amplify, who will update the vehicle position on the map. An IoT rule is also being used to filter critical events that require an immediate attention, such as a vehicle in a high speed or in any other high risk. We filter those messages to send over to another Lambda function that will process and notify whoever is needed through Amazon Simple Notification Service. In terms of monitoring, we are using Amazon Managed Grafana, leveraging its default integration with both Amazon TimeStream Service, where we have now all data about the vehicle's trip, and also Amazon CloudWatch, where we follow some important service metrics, such as API throttling, errors, and limits. This architecture is fully serverless, so we don't need to deal or manage any virtual machines or operational system. Now that you have a vision of the AWS services in scope, let's talk about the security aspects for the solution. Security is job zero and will always be our top priority. In a typical on-premises security model, customers are responsible for the end-to-end security and reliability in their data centers, which includes facilities, power, cooling, hardware, and so on. In AWS, we have a shared responsibility model with the customer, where AWS manages and controls the components from the host operational system and virtualization layer down to the physical security of the facilities in which the services operate. And AWS customers are responsible for building security applications. The level of responsibility, however, for each changes depending on the AWS services you choose to build your solution. If you choose infrastructure services using virtual machines with Amazon EC2, for example, you are responsible to secure everything from the operational system layer that will support your application, which means that you should think about security patches, hardening, updates, OS firewall, anti-malware solutions, and so on. On the other hand, by using serverless services, as we are doing today, AWS takes even more responsibility. Where in that model, customers don't need to deal with the operational system layer or network components. A serverless architecture provides infrastructure security and network isolation by design, which will release you to focus more on your business, application, and innovation. With this, we quickly addressed one of the security challenges that Fernando mentioned before. But you still have your portion of responsibility with security, which include develop a secure application code and validate it with automated CI/CD process, encrypt your data, and manage the access and authorization policies following the least privilege principle. Talking about authentication and authorization, AWS provides a number of different authentication methods to support your requirements. For your IoT devices, you can use client certificates, AWS IAM, or Amazon Cognito. Once the data achieves AWS IoT, the permissions among services are provided by IAM roles and policies. Some carriers use mobile device to track vehicle, so if that is your case, probably you will prefer to have HTTPS endpoints to send your data, and the authentication method will follow your connection pattern. To authenticate to Amazon Managed Grafana, we are using AWS Single Sign-On, and for the web application, we are using Amazon Cognito. With AWS, you manage the privacy controls of your data, control how your data is used, who has access to it, and how it is encrypted. We make it easy to encrypt data in transit and at rest using keys, either managed by AWS or fully managed by you. You can bring your own keys that were generated and managed outside of the AWS. AWS database and storage services provide encryption at rest, which for this solution, it includes not only Amazon TimeStream and Amazon DynamoDB databases, but also geofences collections with Amazon Location and environment variables and deployment packages with AWS Lambda. We easily keep all data in this solution encrypted at rest. AWS IoT Message Broker encrypts all communication while in transit using TLS 1.2, including the connection between the devices and the AWS IoT. All AWS services use TLS 1.2 and beyond to communicate to each other, unless otherwise specified, which means that all data in this solution are also encrypted in transit by default. Still on data protection and data privacy area, it is important to remember to avoid using personal identifiable information to name your resources. For example, don't use an email address, a personal name, or document number as part of your IoT topic or to name your geofence collection. You don't want an IoT topic named with the driver's name or geofence collection with the actual address. So, now that you have a good idea of how the architecture looks like and its security aspects, let's dive deep into each logical flow. Everything starts with the vehicles, or simulated trucks in our case. In a real-world scenario, you can equip your vehicles with sensors or devices that collect metrics continuously, for example, using OBD2 devices to provide real-time data in addition to a series of diagnostic trouble codes. You can connect your IoT devices to our cloud-based service, AWS IoT Core, which forms the backbone for IoT deployments to securely connect all your devices and handle their data at scale. You can not only ingest IoT data to AWS, but also keep a communication among your devices and send back information as needed. In our solution, we are using MQTT as the protocol to send telemetry data from the vehicle devices to an AWS IoT topic or a message broker with AWS IoT Core. All messages go to a topic that includes the vehicle VIN, which we are using as the device ID. MQTT is a lightweight and widely adopted messaging protocol that is designed for constrained devices, but AWS IoT Core also supports MQTT over WebSocket Secure, HTTPS, and LoRaWAN protocols. A soft limit to be aware of is the inbound publisher request per second per account for IoT Core Message Broker, which is currently 20,000 per second in most regions. It's manageable. You can work with AWS support to increase this based on your use case. Check the actual limit for the region you selected. Each vehicle sends a number of different metrics per second, including location with the pair of latitude and longitude, acceleration, fuel level, speed, oil temperature, engine speed, torque and transmission, odometer, and other 5 metrics. But it could be much more. In a real-world scenario, you will probably prefer to send all metrics at once at a more spaced frequency, such as every 5 seconds, once a minute, or even in a few minutes, depending on your requirements, budget, and your appetite for real time. You can even implement a dynamic method that will change the frequency to send metrics depends on the actual vehicle speed. So, if your vehicle is too fast, probably you'd like to send your metrics more often, once in a fraction of a second, for example. If your vehicle is too slow, you'll be okay by sending metrics once in a few minutes. A good idea here would be embed an IoT gateway with AWS IoT Greengrass in each vehicle that would not only process the data and take automated actions locally based on the code you deployed from your AWS environment, but also handle eventual connectivity issues, keeping the solution working even if the vehicle is temporarily disconnected from the AWS IoT. It also can pre-process data and group all metrics before sending it over to AWS IoT. You could also implement a machine learning model that keeps you running at the edge, in other words, embedded in your vehicle. One idea could be implementing a machine learning model to alert the driver about the optimal moment to refill the tank, for example. If you just need to ingest data from IoT devices to AWS with no reverse communication or communication among devices, you can consider to use IoT Basic Ingest to reduce costs and to manage better your quota for the service. With Basic Ingest, you send your messages directly to the IoT rule that I will explain in the next slide, bypassing the traditional IoT topic. Once the message reaches the IoT topic in the AWS IoT core, you can easily filter messages and direct them to the appropriate target by using IoT rules. In AWS IoT, rules are defined using a SQL-like syntax. First example here, we are filtering all location messages related to all vehicles. We are picking the vehicle VIN, latitude, longitude, and timestamp, and send them to AWS Lambda function, where in that Lambda function, we are using Python to update vehicle position and validate geofenced events that Fernando will explain in a few slides. In the second example, we are filtering a critical event directly from the IoT topic to notify operators as soon as possible. In this case, we can easily check if a vehicle is running with a critical oil temperature by using that simple SQL-like syntax. Third example here, we are getting all the messages to store them in the TimeStream database. You just need to include a SQL statement to do that, select the TimeStream database and the table as a target. And now you will have all vehicles data in the Amazon TimeStream. We chose Amazon TimeStream because it's a fast, scalable, fully managed and purpose-built time series database that makes it easy to store and analyze trillions of time series data points per day. It manages the lifecycle of time series data by keeping recent data in memory and moving historical data to a cost-optimized storage tier based upon user-defined policies. It has built-in time series analytics functions, helping you identify trends and patterns in your data in near real time. It's serverless and automatically scale up or down to adjust capacity and performance. Because you don't need to manage the underlying infrastructure, you can focus on optimizing and building your applications. You can easily plug your monitoring system to TimeStream, such as Amazon Managed Grafana. Amazon Managed Grafana is a fully managed and secure data visualization service that you can use for instantly query, correlate, and visualize operational metrics, logs, and traces from multiple sources. The service makes it easy to deploy, operate, and scale Grafana, which is a widely deployed data visualization tool that is popular for its extensible data support. It's integrated with AWS data sources that collect operational data, including Amazon CloudWatch, Amazon Open Search Service, Amazon TimeStream, and others. For user authentication and authorization, Amazon Managed Grafana can integrate with identity providers that support SAML2 and also can integrate with AWS Single Sign-On. We are using Amazon Managed Grafana as our single operational monitoring for all data. We can easily create monitoring by leveraging its integration with Amazon TimeStream that supports a rich SQL-like language. So we can monitor what you saw in the demo and much more. This is an example of a query from Grafana to TimeStream to list the top 100 vehicles in high speed. We are selecting vehicles VINs and their average speed in a given time frame, limiting up to 100 and reverse ordering by speed, so we can show first the vehicles in highest speed. In green, our variables Grafana provide you to make it simpler to create queries. So you don't need to enter your default database and table every time and can use the same time filter you defined for your entire dashboard. In addition to vehicles monitoring, we can include AWS services monitoring with the Amazon CloudWatch integration. So we can follow eventual API throttling, any errors while processing events, service limits, and others. As we mentioned before, there are some critical events that you may want to notify operators immediately. For that, you can filter messages directly from the IoT topic using IoT rules, and use an AWS Lambda as target to process the event and send it over to Amazon SNS that will notify all the subscribers for that kind of event by using email, mobile text, push notifications, PagerDuty, or any other destination supported by Amazon SNS. In that way, important events reach to the right people as quick as the solution receives them in real time. Now, I'll hand over back to Fernando.
Another very important piece of every asset tracking solution is the ability to notify interested parties when assets are inside areas of interest. With Amazon Location Services geofence collections, you can automatically evaluate a vehicle's position against all of the geofences inside that collection. It all starts with the incoming data on AWS IoT Core, as Rafael explained. The arriving data is processed by the topic rule and sent to AWS Lambda, where the geofence lookup is initiated. The request contains the vehicle VIN, which is the asset identifier, and the current position in latitude and longitude format. Amazon Location evaluates this position against all of the geofences in the collection to determine if an asset is entering or exiting an area. If any of these events occur, this event is sent to Amazon Event Bridge, where a Lambda function is triggered and the action is saved on TimeStream for monitoring purposes. This event contains the asset information, the geofence breached, the event itself, either enter or exit, and the timestamp associated to the event. With all of these events, you can calculate for how long an asset stayed within a certain area, if they are outside an allowed location, or even notify interested parties of asset movement. You'd also want a real-time visualization representation of where your assets are. With AWS Amplify, you can leverage AppSync to create subscriptions that will trigger front-end updates in every vehicle movement that occurs. The incoming data is processed by AWS IoT Core, and the Lambda function sends a mutation request to AWS AppSync, which is our GraphQL serverless solution. This mutation contains vehicle VIN and the current location sent. AppSync has two responsibilities here. First one, store the vehicle's last position on Amazon DynamoDB, one of our NoSQL databases famous for its single-digit millisecond performance at any scale. And also, AppSync is responsible for triggering a front-end update on our map, as you saw in the demo. So every time a vehicle moves, you see represented on the map. Now, we have been talking about storing a lot of location data in the solution, and we need to start thinking about good practices that we can implement to avoid storing data that we do not really need. not only from a data volume perspective, but also from a security and privacy perspective. You can see here, from a location perspective, how we can broaden an area to make coordinates more general and less precise by just removing a decimal place. By rounding up, we can aggregate all assets within a radius of a position. One decimal place, for example, is broad enough to aggregate all of the assets within a city. That's about 11.1 kilometers or 7 miles. As we add a decimal place, we get more precise. At 2 decimal places, we can aggregate assets within a town of 1.11 kilometer radius or 3/4 of a mile. 3 decimals can be a facility or a warehouse. 4 decimals could be the lane of a road, and 5 decimals would give us a car at 1.11 meters or 3.5 feet. Amazon Location Service have the ability to store location data up to 6 decimal places, which would give you the position of a cup of coffee, for example. However, you really need a very accurate GPS device to collect such an accurate position. And when working with sensitive data of asset locations, we should design an architecture that only takes what we need to respect the consumer's privacy. We're also improving performance by minimizing lookup queries, and then saving costs by removing query redundancy. We can refer to this as least privilege precision to store and handle only the level of location precision that a use case needs. Moreover, we can generate a cache-friendly identifier using a geocoding system like geohashing. There are a few open source ones out there, but GeoHash is one that is in the public domain. And to bring this back to our use case, a vessel tracking application would want to localize vessels positioned in the ocean. So 3 decimals of precision would suit the requirements really well. For a vehicle exact location on a road though, you may want to add more precision to your query to identify where the car is. And these are the features that Amazon Location provides to you today. With Maps, you can add a visualization layer into any application. Places gives you searching capabilities, geocoding, and reverse geocoding. Routes will give you information on how to get from point A to point B. All of these features are backed by 2 trusted AWS partners, huge players in the geospatial market, Esri and HERE Technologies. Their data currently supports millions of applications on a daily basis. From a privacy standpoint, all queries that are made to Esri and HERE are anonymized, and you can choose which data provider to use with one single API to consume from. So you can basically change providers without changing source code, or creating new agreements with new companies and not even generating new credentials. All you need is an AWS account. There are also no penalties if you stop using the service. Start and stop whenever you want. You also get data ownership on geocoding and reverse geocoding results. You're being able to store them in your own storage services or databases. Trackers will let you send and retrieve real-time batch geolocation information for vehicles, mobile devices, and any other asset that can actually provide their location information. Amazon Location Service this year introduced position filtering as a new option to trackers that really enables cost reduction and reduces jitter effects from inaccurate device location updates, along with the addition of 2 position filtering options. And lastly, you can use geofences in a solution like this to identify areas that are interesting to this particular use case. And that's what geofences are, areas of interest where actions related to geolocations can occur. Geofence collections on Amazon Location provides the capability of detecting enter and exit events on these areas. By providing the current position of a vehicle, these collections are automatically evaluated against all the geofences that they have stored. Once it is detected that a vehicle has entered one of these geofences, an enter event is posted to Amazon EventBridge for further processing. The location evaluation can happen via an API call or by linking trackers and geofencing collections together, really freeing you from calling the API directly. This is great from an automation and integration standpoints. Finally, tracker and geofencing data never leaves your AWS account. That data is encrypted by default at rest and in transit, and you can even use your own keys to encrypt it as well. Now that you've understood the building blocks that we're using to guarantee security, performance efficiency, and operational excellence in the solution, let's talk about a very important piece of every solution that needs to handle events as close to reality as possible: simulating. Rafael showed you before during our demo how this application scales. When you start from 10 or 20 cars, things are very easy to manage and control. Not a lot of compute power is needed at this point to maintain this very small amount of data. Scaling to 100,000 vehicles, however, can be daunting. How can we test with 100,000 vehicles instead of 10? Let me show you. First of all, we created a simulation engine. That simulation engine relies on an AWS Amplify hosted frontend built in React.js. This frontend communicates with AWS via REST APIs that basically create a number of Lambda functions that handles the vehicle simulation processes. The rest of the architecture is virtually the same, as the Lambda functions are now the ones communicating to AWS IoT Core. If you were managing 10 cars, you could easily spin up 10 Lambda functions to represent them. By scaling to 100,000 cars, however, if you keep the same process, you will face issues like timeouts, concurrency issues, and also service limits. On average, we were able to invoke 17.5 Lambda functions each second. And we can try to use a fan-out pattern. So instead of invoking all of them in a single loop, we can create 100 batches that will create Lambda functions that will manage 10 vehicles each, which gives us 100K in total, which is what we need. And we can also have an intermediary Lambda function that will trigger individual workers for each vehicle. We have a scaler that reads a configuration of all tasks that we have to execute and divides them into batches of 100 lambdas, invoking trigger lambda functions, right? We'll pass one batch to each of them. In our case, we'll have to invoke it 100 times with 100 lambdas each. Trigger function receives a batch of requests and invokes vehicles function for each of them. Since each of the triggers will have to invoke only up to 100 workers, it should take them 5 to 10 seconds. Each vehicle function will be responsible to handle only 10 vehicles, so we won't be blocking other processes. You could play with these numbers to achieve the level desired by your solution. But from a cost perspective, you can even reduce the memory and timeout limits for the Lambda functions now. Make sure that you're requesting any service limit increases that are needed on your AWS account to handle a solution like this. And when you're architecting for the cloud, you need to keep API throttling in mind, particularly the types of calls and the frequency in which they are called. When the allotted rate limit for an API call is exceeded, you receive an error response, and the call will be throttled. Excessive API throttling can result in job failure, delays, and operational inefficiencies that will ultimately cost you organization like time and money, of course. Retry logics are automatically implemented when you leverage the AWS SDK, so maybe do that. But you can do it on your own as well, as the pseudocode on the right suggests. In addition to simple retries, each AWS SDK implements an exponential backoff algorithm for best flow control. The idea behind exponential backoff is to use progressively longer waits between retries for consecutive error responses. And retries can be very ineffective if all clients retry at the same time. To avoid this problem, we employ jitter, a random amount of time before making or retrying a request to help prevent large bursts by spreading out the arrival rate. Most exponential backoff algorithms already use jitter to prevent successful collisions. And the last piece of our simulation engine is the dynamic route creation process. When we scale our vehicles, our trigger lambdas generate routes based on origin and destination points stored on DynamoDB. They call Amazon Location to calculate the routes, and store all the polylines in memory, which are used to mimic the vehicle driving process, as you saw on the demo that Rafael showed. We also pick a random point of the route that represents an area of interest, and create a dynamic geofence with a 300 meter radius. So whenever the vehicle enters or leaves an area, a geofence event is presented on Grafana for visualization. And this is our solution. Well, if you want to build something similar, a very good way to start testing your asset tracking solution is by leveraging AWS IoT Device Simulator. It's a one-click deployment process that leverages AWS CloudFormation templates to deploy the solution for you in your AWS account in minutes. With IoT Device Simulator, you can not only simulate vehicles, but also simulate different types of devices with your own desired metrics. It creates an entry point with AWS IoT Core that you can leverage to onboard your own data, like we did in the demo. And that's all we have for today. We'd like to thank you for your presence. Thank you so much.